Gamma Green Solutions has created an Aspen flowsheet simulation for the syngas-to-propylene process. 9 classes of property methods were analyzed in Aspen, and the flexible and predictive equations of state option was selected. In comparing its thermodynamic models, PSRK was chosen as it accounts for high operating temperatures and pressures, as well as its ability to model hydrocarbons, light gases such as hydrogen, and polar and non-polar molecules. When local models were tested, identical results to that of PSRK were achieved, thus eliminating their need. As you can see, the PFD can be divided into 2 sections: methanol and propylene synthesis. A green syngas feed of 33,106 tons per year is required to enter the reactor in order to produce 25,000 tons of methanol. In the FMTP section, 2 reactors may be observed. The effluents of such are purified through a water quench tower, a caustic scrubber, and 5 distillation columns. Such units are employed to achieve 7,316 tons of propylene at 99.5% purity.
Given this overview, a detailed description of the process flow diagram will now be provided and will include Aspen simulation decisions. Focusing on the syngas-to-methanol section, green syngas enters the system and is mixed with the flash drum vapor recycle stream before entering the isothermal Lurgy boiling water reactor. 3 main reactions occur over the enhanced copper catalyst: the hydrogenation of carbon oxides and the reverse water-gas shift reaction. Byproduct formation is not taken into account due to the catalyst's high methanol selectivity, being 99.5%. The equilibrium Gibbs yield and stoichiometric reactors were modeled. Agreeing with literature, results showed a higher level of accuracy for the R-stoich, justifying its choice. The reactor effluent is then cooled to 40 degrees Celsius before entering the flash drum set at an equal pressure of 50 bar. The flash effluents will be composed of 2 streams, vapor and liquid. The vapor phase will have a negligible volume of methanol and water, and a fraction of such will be purged, 3%, in order to reduce the accumulation of inert gases. The remaining 97% will constitute the recycle stream, which must be heated to 250 degrees Celsius to meet reactor operating conditions.
The flash drum liquid effluent must be depressurized to 1.5 bar and heated to 400 degrees Celsius before entering the SEB2 unit, which models the inlet methanol loss as a result of coke formation in the catalyst regeneration unit. The effluent then enters the FMTP turbulent fluidized bed, which operates using the SAPO 1834 catalyst. Different Aspen reactor models were tested, and as the key FMTP reactions are irreversible, thereby discounting the R-Gibbs and R-equilibrium reactors, the R-stoich reactor was chosen given its similarity to literature values and overall accuracy. In total, 8 reactions are considered, of which 5 are side reactions. Meanwhile, the olefin metathesis secondary reactor is another fluidized bed reactor operating at 600 degrees Celsius and 1 bar, where recycled ethylene and butane react over the SAPO 1834 catalyst to form propylene. Side reactions are negligible. Although this reaction is reversible and the equilibrium and Gibbs reactors may be employed, given temperature conditions and literature data confirming a 95 to 99% propylene conversion, R-stoich was selected. The increase in production entails a profit maximization of $2 million per year. As both reactor effluents contain a significant amount of water and carbon monoxide, a water extraction column and a caustic scrubber are used. Both of these units operate at 125 degrees Celsius and 1 bar, justifying the presence of a cooler and depressurization unit. The column was tested as both a flash drum and exhaustion column, with demineralized water as the solvent. Water consumption showed a smaller carbon impact than that of flash energy requirements, leading to the selection of the adsorption column. Approximately 98.6% of the water is removed. With current operating pressures, the use of an absorption column with an aqueous stream for the caustic scrubber will require very low temperatures, suggesting its unfeasibility. Using literature data, this unit was modeled as a SEB2 unit to separate 70% of carbon oxides.
This stream is then cooled to -20 degrees Celsius and pressurized to 30 bar before entering the purification section of the process, constituting of 5 distillation columns. An industry heuristics approach is used, whereby lighter components are separated first. Thus, the first distillation column, C300, separates vapor components such as hydrogen, nitrogen, carbon monoxide, and methane from ethylene and heavier products. The bottoms of this column are at 51.5 degrees Celsius and enter a second distillation column, C301, at 26 bar. Ethane, ethylene, and carbon dioxide are extracted in the distillate and undergo further separation in a third distillation column, C302, operating at 25 bar. Ethylene leaves the top at 95% purity and -23 degrees Celsius. This stream is split in half, part of which is heated and depressurized to 600 degrees Celsius and 1 bar to be recycled back into the R201 olefin metathesis reactor. The remaining 50% is sold, comprising of around 600 tons of ethylene. Going back to the second distillation column, the bottom's product enters a fourth distillation column, C303, at a pressure of 15 bar. The bottom effluent contains mainly butylene, of which 3% is removed from the stream. The remaining 97% is recycled into the metathesis reactor following heating and depressurization to meet reactor operating conditions. On the other hand, the distillate of the C303 distillation column containing propylene, butane, and propane is further purified in a fifth distillation unit, C304. 7,316.2 tons of propylene are collected at the distillate at a 99.5% purity.
The energy integration analysis has been focused on minimizing external heating and cooling requirements and on maximizing internal heat transfer of the process. To do so, the graphical pinch method was used. The temperature of the streams of each heater and cooler were identified and the duties calculated. A value of delta Tmin was appropriately selected based on literature pinch analysis data of various methanol and MTO plants, as well as the use of engineering judgment by analyzing the hot and cold composite curves. As a result, a value of 12 degrees Celsius was chosen. The graphical pinch analysis revealed that the minimum heating requirements of the process amounted to 637 kilowatts, whilst minimum cooling requirements were 1,239 kilowatts. It also revealed that the pinch temperature is 244 degrees Celsius. The heat exchanger network that was designed with the matches chosen is shown here. Following the golden rules for stream matching, 2 matches were found above the pinch and 3 below. 2 matches were deemed infeasible, 1 above the pinch for its cooling requirement and 1 below for its heating requirement. Between the remaining 2 matches, priority was given to the match that allowed for minimum external utility load and best plant layout.
We then integrated our energy analysis into our final case Aspen simulation, with an addition of 6 heat exchangers. Given the extreme temperatures of the process, utilities chosen include cooled water, fuel, and refrigerant Iscian MO89 for its non-ozone depleting characteristics and its lowest GWP potential compared to other ultra-low temperature refrigerants. Chilled water and electricity were not included, as they would result in higher carbon intensity for the process and higher costs. Finally, steam was also not used due to the temperature profile of our hot streams. Quantifying the energy savings due to heat integration, total energy consumption can be reduced by over 42% in the heat integrated case, resulting in total utility savings of $1.2 million per year. Other heat energy savings include standalone column modifications, integrating distillation columns to the back process, as well as catalyst cooling units as a source of heating in the process. Regarding process convergence, despite Aspen showing input translation warnings, reviewing the results summary status page, control panel, and Aspen calculation report indicates that the process convergence was successful with no warnings or errors.